lecture series on real analysis. In this lecture, we are going to prove a theorem on perfect sets. Let us recall what perfect sets are. Perfect sets are the set which are closed and every point is a limit point of a set. Okay, what do we mean by a closed set? Every limit point of the set has to be a member of the set. So, rephrasing the definition of a perfect set, what we have is every limit point of a set is a member of a set and every member of a set is a limit point of a set. Okay, so while talking about the limit points, all the members of the set has to be a limit points and all the limit points of the set has to be a member of a set. This is what a perfect set tells us, right? Here in this lecture we are going to prove a non-empty perfect sets in Rk is going to be uncountable set. Hope you people remember the definition of an uncountable set. A set which is infinite and is not countable is said to be uncountable set. Okay, while saying I have specified a non-empty perfect set. Can an empty set be perfect? Just think for a moment. Yes, it can be perfect because the set is going to have what? No elements, right? So empty set being a finite set is considered to be closed set, right? The set has no limit points, which means E prime is empty. Your E prime is same as that of what? Your E. That is empty set. So empty set is a perfect set under any metric. Okay, here we are going to consider non-empty sets in Rk, which means under Euclidean metric. Okay, on Euclidean space we are going to take some non-empty set and we are going to prove that set is uncountable. Okay, let us start the proof. Here let me take P to be a perfect set in Rk, right? So P is considered to be a perfect set in Rk. That means what? This P is closed as well as every point of P is a limit point of P. So whenever we talk about a limit point, the neighborhood of the limit point is going to contain infinitely many points of the set. Okay, so the neighborhood of that point is going to collect an infinitely many points of the set. Tells you what? Your set is infinite one. So you have proved the set is infinite. Now what should we prove? We have to prove the set is uncountable. So for which we have to say P is not countable. Okay. On the contrary, let us assume P is countable. So when you assume P is countable, then we can say what? Then we can arrange the elements of P in a sequence, right? So let x1, x2, x3, etc. be the elements of P, right? Okay, now what are we going to do is that we are going to construct a sequence of neighborhoods. Okay, let us construct a sequence Vn as follows. In a way that Vn intersection the set P is not empty. Okay, and it has to satisfy certain conditions. That is, Vn plus 1 closure is contained in Vn. Okay, Xn must not be a member of Vn plus 1. Okay, and the third one is Vn closure intersection P is also not empty. Right? In this way, we have to construct the Vn. Okay, here what do we mean by this Vn closure and all? Okay, for example, if I am going to talk V1 to be the neighborhood of x1 means it is going to collect the points in Rk such that absolute of y minus x is less than R for some positive radius R. This V1 closure will denote what? The points in Rk such that absolute of y minus x less than or equals R. Right? In this way, we are constructing the set. Okay? Here, each Vn is going to satisfy this condition, and using the third condition, we may notice that the construction can be held on. Okay? It may go on. Okay? Now, with the help of this only, we are going to proceed further. Right? Here, let me denote what? This Kn to be this Vn bar intersection P. Okay, so what? This Vn bar is what set? It is, by this you may see this is bounded and closed. So when the set is both bounded and closed in Rk, using Heinz-Borel theorem we may say it is compact set. Okay, this P is given to be a perfect set. Perfect set by definition what? It is a closed set. Here we have intersection of compact set and closed set, which means this set is compact. Right? So for each Vn you can associate some Kn. So this is the case that is going to happen when you have xn is not a member of Vn plus 1. This clearly tells you your xn cannot be a member of Kn plus 1 as well, right? So your x1 is present in V1 but is not present in any of V2, V3 and goes on. Okay. Similarly, your x2 is present in V2 but is not present in V3, V4 and etc. Right? So this tells you what? Intersection of Kn is going to be empty. Here, what is this? You have a sequence of compact sets. This construction will give you the same kind of relation, right? A sequence of compact sets, but the intersection is empty. Can it be possible? It cannot be possible at all. So this leads to a contradiction, right? When it leads to a contradiction, the assumption must be wrong. What was the assumption? The assumption was the set is countable. So the assumption must be wrong and we have to come to a conclusion that perfect sets are uncountable, right? If you have any queries in this lecture, you may post it in the comment section. That will be clarified within 24 hours of time. Thank you for watching.